and welcome to our webinar today. Today we will be talking about AC coupled systems with Fronius inverters. Joining me today is my colleague Cyprian Okolo. He's a technical sales advisor for the Western African region. He's based in Lagos, Nigeria. And myself, David Mwangi, the technical sales advisor for the Eastern African region. I am based in Nairobi, Kenya. So we will be tackling the content of the webinar today together, and we will have a few topics to talk about. We will try to answer the questions: what is a Fronius microgrid solution? How does it look like? Where or how does it work? How to successfully set up the system? We are going to look at data communication through the data manager interface. And then we go into zero feeding, at which point then I will hand over to Cyprian. And then after that, he will look at data communication and visualization, design rules. We will also dwell today on Fronius AC-DC coupled solutions, the benefits of both the DC and AC coupled systems, and later on provide you with further information on Fronius products and solutions. So as usual, if you have any questions during the course of this webinar, please feel free to post them in the questions area, and we will do our best to answer all your questions. So let's get started and look at why in the first place to think about having a microgrid solution. So as it starts at the moment, there are quite a number of situations that we are currently facing. Number one is that we are facing an ever-increasing demand for electricity worldwide, and this has been seen also in rural areas, whereby a lot of some of these rural areas are off-grid, and others are in island situations whereby they do not have access to the national grid. We are also looking at most of these off-grid areas as well as islands running off microgrids that are mostly powered through diesel generators. And these diesel generators, of course, consume fossil fuels, which have a cost element to that. And therefore, doing microgrid setups with Fronius inverters can also be a mitigating factor or a way to reduce on the cost of these fuels. So we also are looking at areas whereby we have the national grid available, but we have the possibility of blackouts, or when the situation of the grid is not reliable to a big extent. So therefore, you think of doing a backup system with an AC couple kind of configuration with string inverters and battery inverters. We also have economic considerations, as I mentioned before, with the generators powering most of the remote off-grid situations or areas. The rising cost of fuel is a big concern, as well as the logistics of taking this fuel to these sites. Some of them are quite a distance away, and therefore those come with quite a big cost element. So therefore that means that a PV system can therefore play a big role in mitigating some of these challenges, because the prices of PV equipment have been declining over the last couple of years, and therefore it has become a real business case to retrofit or to integrate a PV system into an existing microgrid scenario, or when one is not in existence, then you can fully power up a microgrid setup with PV only, even excluding a genset in this case. So this map here gives us a rough idea on the access of electricity across the world. But for our case, we want to focus mostly on the African continent. And here we can see the scale here with the color code regarding each country and the access of electricity. So starting from South Africa, which is almost 100%, to some places like the DRC and Burundi, which are at 9% and 19%. So it means that regardless whether some of these countries have high electrification rates or access to electricity or not, we have seen that even with the public grid availability, then we have the question of blackouts or unreliable grids. And in areas where the electrification rate is not very high, then we can think about electrifying some of the most remote areas using microgrids that are fully PV powered. In the next chart, we see the reliability of the public grid in some of the selected countries in Africa. So we here can see the scale of reliability and the likelihood that there is going to be a blackout at one time or the other. But Africa, as an emerging market, has seen high growth rates, and therefore this means that the demand for electricity is also going high. And even therefore, when the public grid is available, the demand on it becomes so high that in some countries they are experiencing load shedding even with high access to electricity. So there is high potential for PV in the African continent. And just like we said before, we have to look at how to save fuel and money and ensure the uptime of the energy supply. So we can also increase and almost realize energy independence by integrating PV power into most, let's say, scenarios that require electricity across the African continent. So when you're talking about now an off-grid or backup solution, we have a perfect match between Fronius and VICTRON inverters. As you know, Fronius traditionally does not have battery inverters, so most of the inverters that you're going to get from Fronius are string inverters. But with the combination of battery inverters, then you're able to realize a microgrid setup. So this therefore can mean that you can both do a microgrid setup with a PV genset solution, as we see with the integration of PV power into a generator grid, or you can do it fully with the renewable energy using the battery inverters and the string inverters from Fronius. So looking at an AC coupled microgrid, we have to start from the beginning and have an understanding of how a normal PV system in the off-grid area works. So in most cases, we have a PV system or a PV array that is connected to a battery charger, in this case an MPPT charger. And then this MPPT charger is charging the battery, then the battery feeds power in DC form to the inverter, and the inverter then changes the DC to AC and feeds the loads. So when you're talking about AC coupling, the reversal of power flow happens in a manner that the available PV power is connected through a string inverter, a Fronius string inverter, and then the Fronius string inverter is AC coupled, as you can see here, to the outlet, AC outlet of the VICTRON inverter charger or other compatible battery inverter. And then the two are feeding the load day and night with available energy. So in this case, as we are going to see later, all the excess energy that is available after supplying the loads then flows through the same AC bus and is used for recharging the batteries. So in some cases, you could have the grid available, as mentioned before, but if you want to do a backup system, especially for, let's say, commercial applications where you require quite a big chunk of storage, then you can also retrofit or integrate this kind of AC coupled configuration with Fronius and a battery inverter. A standby generator is also possible because in some situations, especially in remote areas, there is a possibility that during the nighttime, the batteries can run dry or flat, and therefore you need the possibility that a backup generator can be started to maintain the power supply to the loads. We also have another scenario where we talk about DC and AC coupling within the same configuration. So, and this offers quite a number of advantages, as we are going to see later. So in this case, we have a portion of power from the PV system going through an MPPT charger, recharging your batteries on the DC bar. So this is DC coupled. And we have another portion of power from the PV system going, or PV array going through the PV string inverter, that is Fronius. and a lot of that during the day is directly fed to the loads. If there is surplus at the same time, then the surplus flows through the AC bus and is used for charging the batteries. So the question then is, between AC or DC coupling, which is best? And here you can then try to derive the best of both worlds. So when it comes to AC coupling, as we can see here, that you are generating PV power, and this is then directly going to the loads. Majority of the energy consumption should actually be during the daytime, because you want to optimize on the efficiency of the PV string inverter, because as most of you know that Fronius inverters are operating at above 98% efficiency, and therefore all the DC power that is generated by the PV array is actually converted at a very high efficiency level and directly fed to the loads. So the only slight disadvantage with this setup is that when it comes to charging the batteries, there is a bit slow process, and therefore it's a bit inefficient. Looking at the DC coupling on the other side, majority of the available PV power is stored in the battery system. This setup is very efficient for battery charging, because in this case, the MPPT charger here has a very high conversion efficiency of up to 99%. But when you look at now the power coming from the batteries to the loads, then here we also suffer huge losses. So I think the best battery inverters so far have an efficiency of maybe 92-93%. So therefore, out of 100, you are losing almost 7% of the available power on the DC side. So therefore, it's a question of looking at where the usage patterns of that particular client or customer that you're doing the system for. So if majority of the load is during the day, it's better to do an AC coupled installation. And in this case, we are talking about requirements of power that are above 10 kilowatts. So anything below 10 kilowatts, I think you can use the normal configuration with even smaller hybrid inverters. But when the power requirements are above 10 kilowatts, going into light commercial or medium commercial applications, then you have to think seriously about AC coupling instead of DC coupling. When it comes to the connection of the Fronius inverter in an AC coupled kind of setup, we have two possibilities to connect the Fronius inverter. And one is the AC in, as we see in this graphic representation here. So with the battery inverter, you can connect the Fronius inverter in the AC in. So here, the design rule, as you're going to see later, as far as the design factors are concerned, what we refer to as the factor 1-to-1 rule is not taken into account here. And if there is a grid outage, because in this case, most likely there is going to be a public grid available. If there is a grid outage, then the Fronius inverter does not contribute to the power requirements for that particular duration the grid is out. You can also have now the proper AC coupled configuration, whereby you connect the Fronius inverter to the AC out of the battery inverter. And therefore, here you have to consider the factor 1-to-1 rule. And the inverter in this case would still operate even when the grid fails, if you have a grid connection, because the battery inverter is able to sustain the grid, and therefore the Fronius inverter continues operating. So this is actually the perfect Fronius microgrid solution when you have the Fronius inverter connected on the AC out of the battery inverter. So then how does a Fronius microgrid solution work? So there is optimal interaction between the Fronius inverter and a battery inverter, let's say a VICTRON inverter charger, and it works as follows. So when you have set up everything and the PV array is generating power, you can see that depending on the portion of power that the load is taking, the balance or the excess of that is going back to recharging the batteries. If there is a bit of cloud cover or irradiation levels change, and therefore the PV array reduces the amount of power it's giving to the inverter on the DC side, then the battery inverter from the battery reserves must be able to fill the gap of what is being generated by the PV inverter and what the load actually requires. So therefore, the total amount of power fed to the loads equals production by the PV inverter plus the supplement from the battery inverter. So, but we also have to ask ourselves a very important question, like what happens when the batteries are fully charged? So we can see in this case that the PV array is generating a lot of power, and a lot of this is being charged to AC directly by the Fronius inverter. And in this situation, the load is not consuming a lot of power, and therefore, looking at the battery, we are almost at a near full state of charge, and therefore something should happen. And what should happen is that there must be communication from the battery inverter to the Fronius inverter, informing the Fronius inverter that the batteries are fully charged, and therefore the Fronius inverter should only produce the amount of power that is required by the load at that specific moment. So when you talk about the communication from the battery inverter to the Fronius inverter, we are not talking about a hardwired connection. We are talking about the possibility for a frequency controlled power reduction. So there has to be an automatic power reduction when the battery is fully charged, and this is frequency dependent. So when the battery is at near full state of charge, the battery inverter, in this case the VICTRON inverter, will increase the AC frequency, and with the increased AC frequency, the PV inverter would reduce the amount of power it is producing, or the amount of power it is feeding in to the local grid. So as you can see in this representation, so here we have the state of charge of the battery, and here on this scale, we have the frequency that the battery inverter is operating the grid at. So the next chart shows us the amount of power that is available from the Fronius inverter, and how that is the behavior of power production depending on the frequency. So as you can see, as the battery reaches 90% SOC, the battery inverter will start increasing the frequency, and with every step of increase in frequency, then the Fronius inverter is starting to reduce the power output. So at 52.8 hertz, the production is almost zero, and as the frequency increases towards 54 hertz, it means actually that there is no load consumption, the batteries are full, then the Fronius inverter will almost produce 0 watts in this case. So therefore, this interaction between a Fronius inverter and a battery inverter, the VICTRON in this case, it is very important that there is that compatibility between the operational frequency of the battery inverter and the response from the Fronius inverter for power reduction. So which therefore Fronius inverters are compatible. So we have the Fronius snap inverter series, we have the single phase inverters, we have the Primo 3.0 kilowatts up to 8.2 kilowatts, and we have the small SIMO 3.0 up to 8.2 kilowatts. So these are inverters that are mostly used for residential setups. And we have the bigger three-phase inverters, that is the SIMO 10 to 20 and the Eco 25 and 27 kilowatts. So all these inverters are compatible with the VICTRON inverters because they have been successfully tested for compatibility. So this is both with the VICTRON Quattros and the VICTRON Multiplus inverters. So then how can you successfully set up the system? So the process of setting up an AC coupled configuration on the Fronius side is actually quite simple. What you need to do is to set up the country setup, a special country setup, which is MG50 or 60, depending on your grid frequency. And that is achieved by tapping on the inverter display, the second button from the right, 5 times. And once you enter this code, that is 73887, if you want to change the country setup, then you configure the country setup MG50 or 60 hertz. So this has something to do with the frequency watt characteristics and allows the Fronius inverter also to operate with extended voltage and frequency limits. So once this has been set within the Fronius inverter, the inverter needs to be rebooted for that country setup to fully load in the Fronius inverter. So once now, and this process can also be achieved by configuring the inverter fully for the next steps that need to be configured. And as you know, most of you who have done a configuration using a Fronius inverter, you need to activate the Wi-Fi access point from the Fronius Snap inverter through the display. So you go to the setup menu and then go to Wi-Fi access point, and then once you activate it and have logged in to that SSID and entered the password, then you need to open your browser, preferably Google Chrome, into which in the IP address or IP search bar you're going to enter 192.168.250.181, and that takes you through the configuration or setup wizard of the data manager of the Snap inverter. So if you have a case whereby you have more than one Snap inverter in that setup and you have more than one data manager for the connected Snap inverters, then ensure that there is only one master in the setup, and that can be done by switching the master slave switch for the respective data manager that you want to configure to be master or slave. So as mentioned, it's possible that you're going to do more than one inverter for a microgrid setup. So how you connect the inverters is not different from how you connect them in a grid connected configuration. So you still have to go through the SolarNet ring configuration, and this means the use of Cat5 cables and ring topology from the in and out sockets. And then at the end of the communication loop, you must use the termination plugs. So that those mark the end of the communication loop. And then for each inverter, you need also to configure a unique inverter number. So that is also very, very important, so that the master inverter is able to communicate with each of these inverters, and each inverter serves as an address for the SolarNet ring. So let's now look at the communication interface, the data manager. And as you know, of Fronius inverters, you have the possibility to order a full version inverter, meaning that the inverter comes with a data manager, or you can order a light version inverter, meaning that the inverter does not have the data manager integrated. So for communication purposes within microgrid setup, we would need to connect especially a connection to Modbus TCP terminal, which is an Ethernet cable required here. That would allow you to be able to see the inverter in the SABO-GX or the display of the VICTRON inverter charges, and also to give an internet connection to the data manager, which then would allow you to visualize production data of the Fronius inverters in Fronius SOLAR.WEB. So for communication through Modbus TCP or Ethernet, you have to set up the local area network, and this can be done using any of these methods that we are going to describe here. So you can do as an option DHCP addressing, which means that the IP address is dynamically allocated to the data manager. So if you have a dynamic server present, then you only need a LAN cable connected to the same router that is serving the SABO-GX, and then the Fronius will obtain the IP address automatically from the router. In this case, make sure that the IP switch is on position number B. So there is an IP switch on the data manager itself. So make sure that that particular switch is on position number B. And what is the advantage of this kind of communication? So there is easy installation and can connect with multiple Fronius inverters, and Fronius inverters or the data manager has easy access to the internet. The only disadvantage is that it might take a bit long to search for Fronius inverters, especially when you have a large subnet, depending on how many devices are connected to the same router. Option number B for communicating the data manager via Modbus TCP would be to do a link or local addressing method, which gives the data manager a predefined IP address. So, and this is required when a router is not available. So therefore you connect the data manager directly to the SABO-GX or the display of the VICTRON inverters. And in this case, please make sure that the position of the IP switch is position number A, and then the Fronius data manager in this case is given a predefined IP address, which is 169.254.0.180. So the advantage here is that there is a low risk of communication failing because there is a direct connection, and this can be either through just one cable to the SOLAR.WEB or the connection going through a network switch. So in this case, no router is required. So the disadvantage here is that there might not be an internet connectivity when you have like just a direct connection to the SOLAR.WEB, and therefore, because in this case we also know that, as I had mentioned before, if you have a setup with several Fronius inverters, you can only have one inverter as a master. So you cannot say that you're going to assign internet to one data manager in the same network and have a connection to the SOLAR.WEB from the second data manager. This would not be possible. The third way to make communication between the data manager and the SOLAR.WEB and also give the data manager internet for sending data to Fronius SOLAR.WEB will be the static IP method. So when you have a DHCP server, but you want to give a specific IP address to the data manager, then you put the position of the IP switch to position number P and make sure that the subnet is the same as the SOLAR.WEB, that is within which the SOLAR.WEB is connected, because in this case, the SOLAR.WEB is going to find the data manager within the same network, and then you have to assign that specific address in the right format that you want to give to the data manager. Then here you have to make sure that you also set the gateway and the DNS for the internet connectivity. So what is the advantage here? The Fronius inverter has, or the data manager has, access to the internet, and the SOLAR.WEB can search for the Fronius inverter very quickly within the same network. So the only disadvantage is that it requires a bit more expertise as far as network configuration is concerned. But if you have that expertise, this is actually a very good method for setting up the Fronius inverter to communicate with the SOLAR.WEB as well as set data to Fronius SOLAR.WEB. And at this point, I've come to the end of the first part, and I'll be handing over to Cyprian to do the remaining part of it. So, Cyprian.
Yes, indeed. Thanks a lot, David, for your wonderful presentation. I will now be taking over from this point and, of course, continue with the presentation. So I'll be continuing with this subtitle, which says zero feeding and how that can be achieved in this same microgrid setup. So to set up zero feeding on the Fronius data manager, please ensure that would have to ensure the position of the connection where, of course, where the Fronius inverter or the feed inverter is connected to the VICTRON inverter. So if you could recall from the previous slide, there are situations where the Fronius inverter will be connected to the AC in or the AC out. And of course, we also saw from the slide that David presented the implications of such kind of connections. So continuing, we're going to look at the two scenarios and how zero feeding can be set up. So we have the first option here. If the Fronius inverter is connected to the output of the VICTRON, please ensure that you use the VICTRON ESS, the VICTRON Energy Storage System. And then, of course, you can now go to the Modbus settings of the data manager, that is using the web user interface, and then enter the following settings to ensure that you have it set at TCP, that is for data export via Modbus. And then for the Modbus port, please enter 502. Then the string control address offset should be set at 101. And then for the sound spec model type, it should be set at int plus SF, as can be seen here. And then the inverter control via Modbus should be activated, or should be checked per se. And then most importantly, ensure that you check or save these settings. The settings can be saved by checking or clicking on this icon here. If you don't do this, then these settings would not be acknowledged by the system, and then you won't be able to achieve zero feeding. Okay, so this is very, very important because there are countries and regions where zero feeding is the order of the day, meaning that you are not allowed to feed into the grid. So these settings are absolutely necessary so as to ensure that you don't incur the wrath of the grid operators. So this is how you go about it when the Fronius inverter is connected to the output of the VICTRON inverter. So for the second scenario, when it is connected the input of the VICTRON. So in this case, you can actually do the settings on the web user interface of the Fronius inverter. So you wouldn't have to go through the ESS of the VICTRON inverter, because it is the Fronius inverter that is now the source of power to the system. So first of all, ensure that you make use of the Fronius smart meter, and then enable dynamic power reduction and set it to 0% on the data manager. So we have a screenshot here that's basically explaining what I just said. So on the web user interface, go to dynamic power reduction. And then once you get there, once you scroll down there, you would now select limit for entire system. So this would automatically limit feeding the entire power generated. It will limit it to a particular percentage, but of course the entire system. And then it will ask you to enter the total DC power of the system, which should be entered in wattage and not kilowatt. So if it is 5,000, please ensure you enter 5,000, because there's no kilowatt measurement here. It's all in wattage. Okay, then most importantly, you would now have to fill in the maximum grid feeding power. So this, as indicated here in the second point here, it should be set to 0%. Or as you can see, there's a drop down here because this is a screenshot. It's not active, but then there are two ways you can actually do it. It's either in percentage or in wattage. So, but in both cases, ensure that you leave it at or set it at 0. So once this is done, it would effectively limit to 0 the feeding into the grid. But of course, ensure that you save these settings. Good. Going forward, we're going to take a brief look at data communication and visualization. So these are, of course, very, very important so that we can effectively, through the data communication, monitor and visualize system as it works or functions. So this is, of course, possible via the data communication medium, in Fronius's case, the data manager. And of course, through the data manager, once it's been set up and commissioned, you would now be able to bring it up to the SOLAR.WEB, from which, of course, is a database, Fronius database, from which you can view the performance of the system from wherever you are in the world. Of course, this can be done and achieved via wireless LAN or hardwired via a LAN connection, and of course can be viewed, or monitoring can be carried out on your smart device, be it a laptop, tablet, or even a smartphone. Good. And then of course, you would need internet access to be able to upload these data. So of course, with an internet enabled device, in this case a router, you can of course view this system on the VICTRON BRM portal, or of course, as earlier said, on the Fronius SOLAR.WEB portal. Yeah, so in addition to this, you can also have access to display your system on your screen using the Fronius Solar TV Access portal also. Good. So still on the data communication via the data manager, system data can actually be transferred in parallel to third-party components and of course to the Fronius SOLAR.WEB via the Modbus TCP, or otherwise called Ethernet part or port, Modbus RTU, which usually employs point-to-point connection, and then the Fronius Solar API, of course, using the JSON format, that is the JavaScript object notation format. So just to put it in perspective, we can have connection to our SolarNet ring. So if it is just one inverter, if you have multiple inverter, beg your pardon, you'd now have to connect them via a SolarNet ring. And then, of course, we can now have this setup connected to our smart inverter, of course, via the Modbus RTU. And then, of course, via the Modbus TCP, we can, of course, connect to the VICTRON color display where you can have access to view the entire system in the functional state. But of course, these are also made possible via the router or switch, which provides internet access either via wireless LAN or LAN connection. Good. Just to give you a closer view on how the system is being viewed on the VICTRON color control display, you can, of course, see how the entire system is brought into perspective, coming from the AC input, the battery SOC, state of charge, the inverter functional mode, the Fronius solar power coming in from the Fronius inverter, and then, of course, the power consumption from the load side. You can also have detailed information for a three-phase system and with the respective phase voltage and current as the case may be. So for the VICTRON VRM portal, this is how it looks like. So of course, providing you all the basic information as seen in the color control in the previous slide. The consumption on the load side, the state of charge of the battery, if there's a genset connected, if it is active or inactive, as you can see in this screenshot, it's inactive at this point, and then the solar yield, of course, coming in from the Fronius inverter. Good. Then for the SolarWeb, having a close shot view, you can, of course, have the energy balance. So showing you exactly how energy is produced and consumed for daily, monthly, and even yearly basis. Of course, you can also have your consumption visualized. You can have push service messages, be able to perform remote updates, and then, of course, have other premium features which are chargeable in some cases. But for the sub-Saharan Africa region, the premium version of the SolarWeb is free up till now. Okay, so as David earlier mentioned, we're going to look at design rules. So for design rule, basic design rules for proper system design, please ensure that you obey the one-to-one rule, meaning that the peak power of the PV inverter must not exceed the maximum power of the inverter charger. So implying that the peak power of the Fronius inverter should not be greater than the power or the maximum capacity of the VICTRON inverter, so that it doesn't overload it per se. And then, of course, also have in mind that the DC to AC ratio for the Fronius inverter can be up to 150%. It can be over-dimensioned up to 150%, and which this in turn, of course, should be utilized for more or maximum independence. And then, yeah, for the microgrid setup, please ensure that you select either the 50 or 60 Hz, depending on the frequency of operation for your region or country, as the case may be, because this would, of course, imply or help in the tolerance margin control for both voltage and frequency limits. It will also ensure the automatic power reduction when the battery is fully loaded, just like I described by David in the previous slide. And this is, of course, compatible with all the Fronius Snap Inverter series. And in terms of support, Fronius will, of course, offer support in the system design via our Fronius system partners, technical sales advisors, and of course, via our Fronius tech support line. Good. So if you'd noticed so far, we've been talking about the AC coupling, of course, DC coupling using Fronius and a battery inverter, in this case, the VICTRON inverter. So let's now take a look at how you can achieve this using just Fronius products. So that's where the Fronius Gen 24 Plus hybrid inverter comes into play. So just in brief, the Fronius Gen 24 Plus is compatible with the BYD Premium Battery Box, HVS or HVM. These are the details. We have a dedicated webinar for battery connection and compatibility and commissioning also. So this is just to give us a prelude to AC coupling with the Fronius inverter. So to start off with, we can have it in a backup mode. As you can see in this case, we have all Fronius products. So in this case, we could maybe have an already existing system with the Fronius Snap Inverter, of course, supplying power to the load and of course to the grid, if allowed for your region or country, as the case would be. And then you can now have a battery, the Fronius hybrid inverter that is battery connectable, retrofitted into this particular system, thereby increasing your inverter capacity size, and then of course giving you the option of backup, and of course storing the energy for later use. Then it is, like I said, retrofitable, and meaning that you can either decide to add more PV to expand the system, or you could, if you already have a much over-dimensioned capacity on the DC side. So this is basically optional, so you can have it as an added option. But the most important thing in this case is that you have the flexibility of converting power from AC, DC to AC, DC to AC, AC to DC, and then of course that is charging from the PV point, and of course supplying power from the battery to the load point when we have low or no irradiation, and of course no grid. So just to put everything, or to summarize the previous slides, with the multi-flow technology of the Gen 24 Plus hybrid inverter, we can have power fed directly to the load from the PV point via the DC to AC conversion, and then of course have it fed to the grid if allowed for your region, as earlier said. And then of course, with this same feature of the hybrid inverter, you can of course charge the BYD battery in this case. And then we can of course achieve DC to AC conversion, that is, convert the power from the battery, the DC power to AC to supply the load. And then of course, with the availability of the grid, you can also charge the battery directly from the grid, with the inverter converting the AC to DC. And then of course, you can have it retrofitable, depending on your choice and capacity, and of course AC to AC, DC to AC ratio of your PV module capacity. Good. And to really understand how this works, it's best to go through, or to have a close look at the energy conversion flow. So with this, we will better understand how AC coupled, Fronius only AC coupled or DC coupled system works. Now, in order to understand that, we'll just basically just have a run through the components of a solar system and how it works. Of course, we know we have the PV system or module, your inverter, the load, of course, your smart meter, the grid, and of course, the grid meter. So Of course, we have from the sun, the energy from the sun being converted to AC to be supplied to the load. So we have DC being converted to AC to be supplied to the load point. And then, of course, this same AC can be fed to the grid if allowed. And of course, the function of the smart meter here is to measure the power going or being fed into the grid, and then, of course, power being received from the grid to source the load point. Good. So having said that, let's now have a look at a DC coupled system. Now, for a DC coupled system, let's have a look at what really happens. So for a DC coupled system, as you can see, the battery is directly connected to the inverter via the DC line. So energy flows directly from the PV source, per se, since it's DC power, to the battery. So there's basically no conversion here. So it's just basically regulation of power to the battery, because the inverter is already integrated with MPPT charge controller. So it controls or regulates the power being fed into the battery, so as to ensure that it satisfies the SOC regulation or the SOC specifics. Good. Now, from this same DC, the inverter can, of course, convert this DC to AC and then supply the load point. So this is basically what a DC coupled system is. And then, of course, during less irradiation or no irradiation, you can, of course, have the power fed back from the battery to supply the load. That is when needed. So the energy stored in the battery can now be converted back to AC and then fed to supply the AC line. Good. Now, going to an AC coupled system, as you can see in this case, the battery isn't connected directly to the PV inverter. So we can, of course, now go ahead to say that that's how you can basically differentiate between an AC coupled system and a DC coupled system. So if we take a step back to this DC coupled system, we can see that the battery is directly connected to the inverter on the same DC line. Now, coming to the AC coupled system, we can now see that the battery is not connected to the PV inverter. It is rather connected to the AC line or the AC bus of the system. So that's basically how the system stands to get their name. So it's basically dependent on how how the battery is connected to the PV inverter. So the battery connected to the PV inverter via the AC line, but of course, with the use of a battery inverter that converts the AC to DC, because the battery uses or can only store DC power. So for an AC coupled system, we now have DC being converted to AC to supply the load line, and then of course the same AC being converted by the battery inverter to DC to store energy in the battery, and then of course when needed, this DC is now converted to AC to supply the load. So one would now ask, what would be the benefits of DC coupling? I'm sure we've already seen that from the slides being presented already by David. We'll of course just put this in perspective using the Fronius only system. So for these benefits, we can better understand it by having both systems juxtaposed. So from here, it basically has to do with first off the system efficiency. Now, for a DC coupled system, as you can see in this case, there's just only one. There's just one conversion, energy conversion in this case, because for DC to DC, it's just basically regulation. DC power just gets regulated and then stored in the battery. But then to have it being used by the AC load line, it will have to be converted to AC by the inverter, of course, to be used by the load. So there's just one conversion from DC to AC. But for an AC coupled system, we have several conversion processes happening. So first up, it's the DC to AC from the PV to the load, and then we have the DC to yeah, for the DC to DC, I mean AC to DC, sorry. So AC being converted to DC via the battery inverter, and then of course the DC to AC. So that is while converting the energy stored in the battery for later use by the load line. So we have 3 conversion processes, and mind you, the higher the conversion, the lesser the efficiency. So we have yeah. So there you have it, the basic difference between the DC and AC coupled system. So this is, of course, one of the benefits of a DC coupled system. And then we can also have here that we can make use of the true, one of the very important feature of the Gen 24 Plus inverter, the true 3-phase backup with the SIMO Gen 24 Plus with power class 6 to 10 kilowatts. So with this, you can actually have true 3-phase backup, meaning that you can get as much as the inverter capacity as your backup. And then this is actually a pretty good advantage that the Gen 24 Plus hybrid inverter has over other such competitor products. Good. Also, as an advantage, you can have more PV capacity on one phase. So mind you, with the DC battery inverter, this of course increases the inverter capacity, because the inverter capacity basically takes note of the capacity of all the inverter in the system. So if you have a DC or battery inverter in the system, it of course has an accumulative effect on the battery capacity. So why I'm saying this is because for some countries or region, we have restrictions for single phase system. We have countries that actually have a power capacity cap of 10 kilowatts, for example. So if you have a capacity cap for single phase or 10 kilowatts, it means that you can only have 10 kilowatts worth of inverter in that particular system. So if you're making use of the Fronius, a 10 kilowatt Fronius inverter, it means that you can have as much as 15 kilowatts power capacity from the DC, that is taking into cognizance of the 150% over dimensioning ratio. And then this, of course, would improve your self-sufficiency level. And then now comparing it to a situation where you have a DC or battery inverter, it means that, say, if you have a 5 kilowatt battery inverter, it now limits the capacity of the PV inverter you can use in that system to 5 kilowatts. And then since that is 5 kilowatts, with 150% oversizing, you can only have 7.5 kilowatts PV on your PV array. Good. So these are the benefits of DC coupled system using the Fronius hybrid inverter. So of course, let's take a look at the benefits of AC coupling. So for AC coupling, of course, it's easily retrofitable, meaning that since the battery is not connected directly to the PV, it means you have the flexibility of connecting different kinds of battery to this particular system. So you're not actually restricted, because to connect a battery directly to the hybrid inverter, first off, it has to be a hybrid inverter. Secondly, it has to be compatible with the battery. And then we're talking about a high voltage in this case. So it has to be a high voltage battery that is compatible with the hybrid inverter. But in this case, there is no such restriction. So meaning that you can connect different sorts of battery to the AC line, of course, using the battery inverter. And then added to this is that, well, for some clients or for some installers, they may have a particular feature of the battery monitoring system per se that they would love to, to keep using. So this might be one of the reasons why they would want to, employ the AC coupled old system. Of course, it now comes as an advantage. Good. So it brings us to the end of the presentation. Just to inform you that we have lots of content available on our homepage. We have operating and installation instructions via this link. These are downloadable information. You can also visit our YouTube channel where we have lots and lots of how-to videos and of course webinar recordings, especially the ones we run on our Sub-Saharan Africa playlist. So through this link, you can of course have access to these webinars and then have a look at them for reference purposes. And then of course you can contact our technical training, sales and after sales team through this contact details. But more specifically, if you want to get in touch with us, the TSAs, you can of course contact Byron, TSA for Southern Africa, myself, TSA for Western Africa, and then of course David Mwangi, who is the TSA for Eastern Africa. So at this point, I'd want to say thank you very much for staying tuned and attending the webinar. And this is wishing us the best of all. Thank you and goodbye.